of this afternoon, Leandro de Souza from UFABC. So also Flávio is from the Dense and Carries program. He's going to speak about the latest advances on hematites designed by chemical route from lab to industrial scale. The stage is yours, Flávio.
Okay, thank you very much, Anna. Good afternoon, everyone. Before I start, I would like to thank the organizing committee for giving this opportunity for me to share some of our recent results with you guys today. But I decided, because I just have a 15-minute or less talk, to move to change the title a little bit, just to focus my presentation as recent results. Then I will talk a little bit about the back contact interface that we are exploring right now in between the FTO and the photocatalyst. But this you also have a big implication in the large scale production. This is the outline of my talk. I will give you a brief introduction about the main target we have here, and also the methodology. I go through the results and then give you some conclusions and then acknowledgement. Just jump to the quick introduction for you to understand. We have been working design photoanodes for photoelectrochemical cell. I think my colleague Claudia already gave you guys a big overview about how the photoelectrochemical cell works. But the main target that we are focused is to understand a little bit how to manipulate or control the interface that we have during the film design. As you see here, we have three different interfaces, which we can say that we have three main recombination pathway to control. And then this will be related direct to all these parameters that govern the photocurrent efficiency in photoanode materials. In these last 3 years of research project with the P5 team, we have been working with the with the solid liquid interface using a co-catalyst, and then we have some success on that. And then we move inside of the system, the photocatalyst, to work trying to increase the electrical conductivity by doping or segregating elements in between the grains. And right now we just focus, if you want to go over in the scale, produce large scale materials, we need us to avoid the electron loss by the exposition of electrolytes. And then, of course, we choose two model system, which the first one is the photocatalyst, is hematite. We do have a lot of challenges on hematite yet. It's a nice material to perform the really fundamental investigation. And then the other ones is the chemical solution. When you prepare a polymeric solution, then perform the thermal treatment, you see that we can have a lot of problems in terms of cracks and adhesion and all the contact. You need to have a good contact in between the photocatalyst and the substrate. Also, you need to have the effective charge separation. And then we have been working with the easy and scalable process to do that and to think about in future for large scale materials. And then here is the typical chemical solution process where you prepare a polymeric solution with the precursor that you intended to prepare the photocatalyst. Once you have the polymeric gel or polymeric solution, we just in water, all this is made in water. And then what we decided to do is to control the viscosity. And then we start to have a success on that. What we did, we reduced the content of water in the solution, and then we replaced this water by, and then in this stage, we just replace the water, the content of water by a mixture of alcohols. And in the same stage, we add some zircon precursor. The intention behind of this modification is because we want to have a different polymer configuration or polymeric solution configuration. which may have a better molecular packing when we are making the deposition over a rougher morphology, as we have this commercial FTO. And during the thermal treatment, for the elimination of the organic part, if we have a success in adding the zirconium goes direct to in between the grain and suppress the grain growth, and maybe release or reduce the stress in between the competition in between the FTO and the grain growth. This probably you reduce this stress, you make a better layer conformation, let's say like this. Okay, and then just to show some results, and then I can jump direct to the results for you, just to avoid to miss more time. This is the typical morphology that we have in the commercial FTO. Is very rough, is very regular morphology. And then when we add ours, we have, when we don't change or we don't modify the original precursor solution, this is in water or ethanol with just a single solvent, we see that the top of the FTO morphology is the only one in contact with our layer. Maybe the stress is too big, is too strong in between, then the position of we don't change or we don't modify the original precursor solution. This is in water or ethanol with just a single solvent. We see that the top of the FTO morphology is the only one in contact with our layer. Maybe the stress is too big, is too strong in between, then the position of the solution or the solution starts to be removed during the organic elimination. But if you go through the current strategy, we see that we could really reduce this competition in between the grain growth and the FTO, which we believe that now the only one that guides the crystallization, the grain growth, is the FTO, probably. This is the main idea that we have. But just to give you a little bit more detail and confirm that we just dig deep inside of the nanoscale interface, and then you see here the high resolution transmission electron microscopy image for the pure system, the system without any modification. And this, the bottom, you see all the modifications. If you see the reconstruction of the diffraction electron image, you can see that this is very irregular and interface in comparison with the one that we have this better molecular packing. Also, when we reduce, if the zirconium segregate as we expect, the reduction occurs, and then you see a better and behavior interface. Then we made some estimation, and then we see that the interface interaction in between the FTO and the photocatalyst layer, the hematite, is 3 times higher in the pure system in comparison with the one that we modify with our new strategy, which means that we could reduce, not release, but reduce this competition in between the FTO and the grain growth, because then this can avoid some FTO exposition and electrons. And then just to make sure that we are talking through for you, we just take advantage of the sample preparation, and then we just perform scanning transmission electron microscopy together with EELS to give you a chemical map. This we do have 3 important information. The first one, we see only the tin, which is the FTO, the fluorine doped tin oxide. Then you see here the tin remain in the FTO without diffusion, as usually claimed in the literature. The zirconium is interesting. It's segregating between the hematite grains, and of course the iron is spread out in the entire sample, a part of the FTO, of course. And then, of course, we add some co-catalyst. And if you think to increase the performance of the system, we already take the advantage of the best electrode, and we electrodeposit some nickel co-catalyst. And you see that it's remain only in the surface exposed to the electrolyte. And then just to confirm that the system or the strategy work, you see here a photoelectrochemical test. When you check the photocurrent, we see that the optimization of zirconium achieving the highest performance with 3%, the addition. And then we see some incrementing performance by adding the co-catalyst as expected. And the most important results here is not only the performance, but the gain that we can do, or the gain that we have by manipulating individually each parameter without lose the gain we have for each step, which I'm trying to talk to you is we can manipulate the interface of the electric conductivity, increase each one of the parameters without lose performance when we put all together. And then we just added some whole scavenger just to see if this is the end for the material, we can improve a little bit more. And then you see here the blue curve. We still have plenty of investigation to be done in order to increase even more the performance of the system. And then just to summarize my talk, I don't know if I passed through the time right already, but this is important, it's a big deal for us because now we could be able to manipulate the three interfaces, and we not only could manipulate individually each of parameters that govern the photocurrent, but right now we can put all together and have a performance performance of all these parameter controlled, which means that we can go over in large scale production, as you see here. Right now we are investigate bigger area because now we can control those three electron laws by the FTO exposition. With this, I would like to just to say thanks to the P5 team, all the people are involved in the work and the international collaboration, and for CINE, of course, for all the support and all the sponsors. And thank you very much for the kind attention. I'll be happy to take any question if you have.
Thank you, Flávio. But I have one. Mm-hmm. So about this large scale systems, mm-hmm. What about the challenges? Can you just comment? So I'm sure that there are many challenges when you go from lab to like, let's say a prototype, large scale, but in your opinion about the challenges, can you, I don't know if you can just like a rank. Then, run. It's going to be the position of the photocathode, the photoanode, the membranes. I mean, just can you comment on that?
Yeah, I think the most challenge that we have, since we can believe that we have good engineers formed in Brazil, I think that the most hard one is to keep the efficiency that you have in small scale to the large scale. And I think the big issue that we have is this loss of electron that usually we don't know, because when you see the covering of the layer over the substrate, it's okay. If you see the scanning electron microscopy, you see it seems like it's good, but if you go inside the system or the interface, you see that only a few regions are in contact with the FTO, and other ones can be like, you know, the challenges, you have to use mesoporous, let's say morphology, to use the aspect ratio of the nanometric scale. But this is a problem as well, because of course, some parts of the FTO will be exposed to the electrolyte. Then I think we have this kind of ghost loss that we cannot control. this is responsible for, usually in the small scale, it's okay, we can control, it's not the big deal. But if you think in large area, this exposed FTO or this missed contact, you'll be very big in terms of efficiency. And then for me right now, if I would rank, this can be the most challenge problem that we can face and overcome for large scale. The other ones is, of course, is engineering stuff, but I think we can surpass this, not easily, but we can do that. But right now, to keep the efficiency that we gain in small area, it'll be hard to control this, I think.
Thank you. It's the same problem with the perovskite solar cells.
Yeah,
I think it's
so.
because when you have this kind of pinholes in the film have increased in charge recombination. So this, I think, it's a problem. It's not only in the photocatalysis, but also in
is not only charge recombination, it's electron loss. We even know where the electron goes, because we believe that the electron are, being transported to the cathode to reduce the water. But yeah, this is interesting.
So this is the first one. This also is the first one in my hand when you think about scaling up our solar cells in the lab. So thank you, Flávio.
Okay. Thank you, guys.
Very nice
Thank
talk.
You,